Hi, I'm Dr. A.J. Kumar. This is Abstract Algebra, I think 18 maybe? It might be 19, not sure. It might be 17. So, on Gab and on Twitter and everywhere I have social media, I have this as my banner picture, this picture. And it shows 3 lines and 3 points. And can I see the full picture? Yeah. And notice there seems to be sort of some weird duality here. So there's a yellow point and a yellow line. There's a pink and a blue point that are both on the yellow line. The blue point seems to be paired with a blue line, which has a pink and a yellow line. And then there's this ellipse that's sitting here with sort of 4 points on them. And you can kind of see how if you do some kind of weird line drawing projection thing, you can sort of construct these 4 points. And my goal in this little upcoming mini-series, so generally we're aiming towards geometric algebra. There's sort of 2 threads in my abstract algebra playlist. Number 1 is just sort of getting through abstract algebra, but also I have sort of an eye towards what I'm wanting to do with QAnal. And specifically I want to get into geometric algebra. And the most important idea in geometric algebra is something called, duality. And this is a interesting, simple way to get a hands-on experience with duality. This construction, this presentation I more or less stole from Weilberger, but this construction goes back to the ancient Greeks. And I'm also going to try to figure out a way to share the GeoGebra file, and I put it on GitLab or I need to get my website back up, so this might be motivating for me to do that. Anyway, I made this in the painting program. Now notice over here I have a circle and a point, and over here I have an ellipse. So it doesn't actually, you don't have to start with a circle, you can do any conic. And I'm going to trace this back and show you how this is sort of relevant to the 2 threads are part of the same program, so if that makes sense. But anyway, let's just get started. So this is, at the end of this little mini-series, I want you to fully understand and appreciate what's going on in this picture. But for now, let me just explain something called how to find the polar. Now, there's a simple way to find the polar in GeoGebra, which is to find the polar or diameter line, and that's the polar. Okay, and if you had pulled up that picture, the yellow line was the polar with respect to the ellipse of the yellow line, and so you can start with the line and derive the point as well, and that's called the polar. And then that was something called I can't remember. I think it's called the polar duality theorem, something like that. It's or the polar triad. I can't remember. I don't remember the names of theorems. I remember what the theorem says. But anyway, that's the loser's way to find the polar. There's another loser way to find the polar, which is to construct tangents. So you pick the point and you pick the conic, and then you get 2 tangent lines going through the conic, and then you join. So you find the meet of the tangents and the conics, and then there will be 2 meets, and then you join those meets, and there you have your polar again. That's another loser way to find the polar. But it's also not clear how do you reverse engineer that process to go from the polar. You just have some random line, and okay, you know what? Let me show you that. Let me actually go back to this construction, and then let me do the meets. So we found the tangents. Now we have the meets. Join those 2 points. Okay. Now, this is fine, and you can kind of see how this works and how it's funny, we can't quite get a diameter. right? We get something that's very close, and then as the point approaches the conic, the polar approaches being a tangent, but then if we're on the conic, it disappears, and if we're inside, then we sort of get something else. And so it's kind of interesting, but also the polar is also equally well defined inside of here, but not with this construction. So I'm going to show you a different construction, the winner's construction, not the CIA's construction. So instead what you do is you just pick two random points on the circle. It literally does not matter which points. Okay? And I'm going to make these, first of all, don't show the label. I'm not very good at GeoGebra. Okay, I'm going to make these points bigger so that you can see them. And I'm going to make one of them like blue. That's an ugly blue. That's a prettier blue. Yeah, that's fine. I'm going to make another one orange. Why is it opening the window over there? What's an orange that isn't ugly? Yeah, that's good enough. Okay. That's fine. Now, I'm going to join my just two random points with the original blue point. And let me make these smaller. Should I make these... Why is it opening it all the way over there? That's so stupid. Like, why? It's not useful to me over there. Anyway, let me make these a little bit smaller. Make them 7 instead of 9. Really? Okay. Now what I'm going to do is I'm going to find the other meat in both cases. And I wish that... Are you kidding me? Okay. I'm going to make these hollow. Don't show the label. Don't show the label. Okay. So I have 4 points here. Oh, and I wanted to make this one orange. Orange. You wonder why I say I hate computers, and this is why I hate computers. Okay. So, we have two of our... If you instead imagine that we had started with these 4 points, I've now I've formed 2 of the possible joins, but there are 6 possible joins, I think. 4... It's 4 choose 2. So I think that's 4 factorial over 2 factorial times 2 factorial. So that is 12 divided by 2 times... It's 12 divided by 2 times 2. That would indicate that there's 3. I don't know. I probably did something wrong there. Anyway, what my point is I'm going to do the 2 other... Yeah, there are only 3. Okay. I'm going to do the 2 other types of joins. There's 4, and I'm choosing 2 of them. I'm not very good at combinatorics. Anyway, so what I want to do first of all is, for fuck's sake, I'm gonna fucking kill this loser program. Okay. And Jesus Christ. Unbelievable. Anyway, now instead what I'm going to do is, okay, so now I found some meets, or I don't even remember what we're doing. Finding the polars. That's right. I want to I want to find the meets, the two additional meets now. And okay, so now you won't construct a point when I click randomly, but before, what are you even doing? Make a point. I want a point there. Jesus Christ. Unbelievable. Unbelievable. Okay, I'm not going to mess with the type of point. Okay, but I am going to make this 7. If anyone knows how to get it to not do the labels are just so annoying. Why? Okay. Now, I also want to, here. This is my point. This is the most frustrating program to use in the entire world. Okay, and I want to highlight this. Color, and I want to make it this kind of deep blue color. Okay, finally, Jesus Christ. Okay, this is the same line that we had before. Notice that these two joins are kind of moving, where the two black points are, they kind of move around. But notice that the line that we construct doesn't depend on these 2 points on the circle. So it will construct 2 different control points. I don't have a word for them, control points. It'll construct 2 different points right here, but the line it constructs is independent of where these orange and pink points are. And now, if I take this point and move it inside the circle, we also have a perfectly well-defined polar outside of the outside of the, you know what I mean. Notice that the solid colored points are not moving, but the hollow ones are, because those are dependent on right, so this orange point is the join of, or whatever, join the navy point to the orange point, and then find the other intersection, that's the hollow orange point. Join the navy point to the bright blue point, and the hollow bright blue point is the other point of intersection. And that works just as well outside here. Okay, so that's the pole. So the line is called the polar, and the point is called the pole. And the next video, what I'm going to show you is, given the polar, given the line, how do you find the point? So every point, there's only one possible line to construct. And I'll prove this once we see how this works algebraically. Notice it's interesting that this, if I move, there's this little black point down here at the bottom, and I can move and suddenly it'll show up on the other side. And that's kind of interesting. Anyway, I'll try to keep this, I'll try to include this GeoGebra file. I'm sorry I got so frustrated, but anyway, and it also works for tangent lines, which is kind of cool. It'll construct a tangent line. In fact, one of the... That's weird. I don't think it would work if it's exactly tangent, but anyway, so yeah, this works. And it's not clear why this works, but we'll see why it works. And when we do an algebraic framework, which is called projective geometry, then it'll be obvious why this works. But it's sort of just, this is something, I think Apollonius came up with this idea, and that he was, this is ancient Greece, and he was obviously not using GeoGebra. Anyway, this is sort of the point. The point is, what I want to talk about is duality. That's the important idea, and the idea is that the point and the line in this weird framework, which I'm only showing you a little bit of, sort of hinting at, the point and the line are inherently dual with respect to this red circle. Now, I could have taken this red circle and made it an ellipse. Hey, I wonder if I can do that. Let me make it an ellipse just to show you. So I'm going to make it 3y squared. And you see with an ellipse, it works exactly the same. And, oh crap, how do I make a... I can also make it a parabola. Just delete the square off of y. That'll make it a parabola. And you can do the exact same construction and it works exactly the same way. And then, let's try minus 3y times x times y. Does that make a hyperbola? It does. And then with a hyperbola, exactly the same construction. Doesn't matter where these 2 points are. I will construct the exact same polar line, so it doesn't matter whether this conic is a parabola, a circle, a hyperbola, or there's one of the parabola, hyperbola, ellipse, or circle. Those are the 4 types of conics, and a circle is obviously a type of ellipse. Anyway, there's a lot going on just in this picture right here. There's so much richness. And I'm gonna be able to hint at little bits of it for a while, and I'll try to share this GeoGebra file. So anyway, I'm stopping the video. Thank you for watching. Sorry about all the cursing. Yeah, thank you. Stop recording.